My name is Claudio Imbrenda. I work for IBM, and I do QEMU and KVM development. And today I'm here to talk about our new architecture for protected virtual machines on s390x, or the mainframe architecture from IBM. This is the overview of the talk, and let's start. What is this all about? This is about protected virtualization, that is to have virtual machines whose state cannot be observed or altered by the hypervisor. So, why? Well, security. If you don't trust your operators, if you don't trust even your cloud operator, or if you don't trust the hypervisor to not be buggy, or if you don't care about any of that, if the law forces you to care, then you might be interested in this. So let's see how we do it. This is the big picture of the whole protected virtualization. So we have guests, we have the hypervisor, and we have a new entity which we call the ultravisor. The guest is trusted only for itself. We assume that the guest will not shoot itself in the foot, but the guest is free to shoot itself in the foot if they so wish. We do not assume that the guest is not malicious, even protected guests. The hypervisor is untrusted. We do not assume anything about that. And the ultravisor is trusted system-wide. These arrows here show access patterns. The hypervisor can, of course, access the memory of normal guests. Normal guests normally cannot access the memory of the hypervisor, but if the hypervisor is buggy or malicious, that could be possible. Nobody can read or write into the protected guests, except for the ultravisor and the protected guests themselves. Here there's an asterisk. I will explain later why. This means that the ultravisor is the omnipotent entity above everything. Yes. So, ultravisor is a trusted entity. It's implemented in hardware and firmware, and it needs to take over some of the tasks traditionally performed by the hypervisor. It does decryption and verification of the boot image of protected guests, and protects the guests from the hypervisor and from the other guests, secure and non-secure guests, and proxies all the interactions between the guest and the hypervisor. Protection means that the guest memory is not accessible by the hypervisor unless it is shared. And this is the asterisk it was in the picture earlier. Protected guests can only access their own memory. There is no way for a protected guest to access any other memory except their own. The guest decides which memory to share with the hypervisor for I/O, because otherwise you have a very secure guest, but not very useful one. The important thing is that it's the guest that decides, of course, which memory to share with the hypervisor, and that's the only memory that the hypervisor, the only part of the protected guest that the hypervisor will be able to access. The guest-to-host mappings are secured, which means that the hypervisor cannot do any tricks of remapping guest pages to different addresses. Can try, but it will not work. And finally, the ultravisor checks and verifies the interaction between the hypervisor and the guest. It's not just a blind proxy between the guests and the hypervisor. It also performs some verification and some checking to make sure that the hypervisor is not trying to do anything fishy or violate the specifications. So what's left then in the hypervisor is I/O and device model, so the actual reading and writing from the disk, for example, or network traffic, all scheduling. This, of course, means that we are not doing anything against any potential denial of service attacks. Of course, the hypervisor is free to not schedule the guests, or the operator could just shut down the server or pull the plug, so that's pointless. Memory management is still, of course, performed by the hypervisor. housekeeping for some instructions. As I said before, the ultravisor takes charge of some of the tasks that were traditionally done by the hypervisor. Some instructions, for example, will be handled by the ultravisor, but in some cases, some instructions need to be after they have been handled by the ultravisor, the hypervisor needs to be notified that they have happened. And many instructions are still completely handled by the hypervisor, for example, but not only all the I/O instructions. So let's jump and see how this looks like in practice. Let's have a look at the life cycle. What happens when we try to start the hypervisor and when we try to start a protected guest. So the first thing is to check if the ultravisor is available and query the ultravisor to determine which characteristics, which feature it has, and which parameters which will be needed. For example, in step 3, the hypervisor is to opt in. Without this opt-in, it will not be able to start any secure guests. And to do so, it needs to donate some memory to the ultravisor. The amount of memory is communicated exactly in step 2 during this query ultravisor, among other things. Okay, so the hypervisor has started and has opted in. How do we start the secure guest now? The secure guest puts in a standard non-secure mode, and then this standard guest will then perform some interesting actions. First, it will need to load an encrypted blob in memory, unless it's already there. If you start QEMU with the -kernel option, then it will already be in memory, no need to load it. Then the guest will perform a reboot into secure mode. It's like a reboot, except that instead of specifying a specific device to reboot from, it will specify kind of that the blob is the device to reboot from, and then do a secure reboot in secure mode or protected mode. At this point, the hypervisor will issue the appropriate ultravisor calls to set up a protected guest. For example, creating a secure configuration, which will create the instance of the of a protected guest, create secure virtual CPUs, so create the single instances of each of the virtual CPUs that are needed for the protected virtualization, and then set configuration parameters, in which basically the hypervisor is passing this blob taken from the non-secure guest directly and basically given directly to the ultravisor. At this point, the hypervisor will unpack this boot blob, which means it will ask the ultravisor to decrypt all of the blob. Of course, it's not just going to be decrypted, it will be protected and then decrypted. In this way, the hypervisor will never be able to read the content of the boot blob, which could contain secrets. This is done with a public key. The private key is safely hidden in the hardware. And at this point, the hypervisor just continues running the guest. It just has to switch the format of the CPU control block used for the virtualization for the VM start, basically. I talked about memory donation. During the life cycle, the hypervisor will need to donate some blocks of memory, contiguous memory, to the ultravisor. The ultravisor-based storage, in particular, can be very big and needs to be in absolute storage, which means physical memory. So it needs to be a big block of physically contiguous memory. The size depends on the size of the host memory, and this can be big. So this should be done probably at the very beginning of the boot process of the hypervisor. Otherwise, it will not be able to find enough memory to allocate this big blob. The other ones are easy because the one per VM and the one per CPU, these ones are small, so it's not a problem to find them. This one, configuration virtual storage, can be big, but it needs to be contiguous in virtual memory, so this is also easy to find during runtime. So, how do we handle instruction interception? First of all, many of the fields in the CPU state description will become reserved and unused because we don't want the hypervisor to be able to look into those registers or other state. There are different interception codes than normal because we're not performing normal interception and normal instruction interpretation, but it's protected, so it's some things need to be done differently, so we're telling the hypervisor that this is not a normal thing. In some cases, there's a differentiation because, as I said before, some instructions have to be handled by the hypervisor, some will be handled by the ultravisor, but the hypervisor has to be notified about it. Like, let's say, store prefix, if you know what I'm talking about, you will understand why. On the other hand, some instructions have small buffers. It's not practical to expose the whole page because then you would expose some other memory that is around these small buffers, so it would be impractical. On the other hand, forcing the guest to use an explicitly secure, an explicitly shared page to store those buffers used for these instructions would also be too much of a burden on the guest side, and one of the goals was to minimize the impact also on the guest. So we have this secure instruction data area, which is some kind of a small bounce buffer, which is used for bouncing these small buffers between the guest and the hypervisor and back when needed. This secure instruction data area is in the hypervisor storage. Interrupt injection, we usually just read the interrupt vector. For the interrupt we have to service, then we write in the right interrupt return address vector what is the return address. We have to jump back after we're done with the interrupt, and that's how we do interrupts normally. We cannot read or write in memory anymore, so this is not possible. So we have to go through the ultravisor, and we do this in particular through the state description. There are specific bits and that can be set to indicate to the ultravisor that when we resume executing the CPU, that specific interrupts have to be injected, and the parameters will be placed in the same locations as where you find them when you actually get an intercept, so when you're going in the other direction normally. Not all interrupts are always allowed. In particular, program interrupts, so exceptions, are only allowed to be injected when we are interpreting or emulating a specific instructions that we expect that can possibly generate those interrupts, and then only those interrupts can be injected. And of course, it's not allowed to inject any interrupt that has been masked, because that's the whole point of masking it. So what changes in the state description is interception parameters. Normally, we find there the text of the instruction that generates the interception. This will be normalized. So if the instruction uses register 5 and 6, and another time it uses registers 7 and 12, you will always see 2 and 3 here, no matter what. The general registers are also saved into the state description, only on when needed, so on a case-by-case basis, depending on which instruction is to be handled by the hypervisor. Those registers are also saved in a normalized location, and it's in the same normalized location that is indicated in the instruction text, so the hypervisor will not be confused. And when appropriate, they will be copied back to the correct guest registers. This also means that when exiting from the VM, the registers will not contain anything. The actual registers will not contain anything. That's different from what a normal the normal emulation works on s390 normally. For the control registers, we only see the interrupt-related bits, so which classes of interrupts are enabled, because the hypervisor needs to know which interrupt it's allowed to inject or not, to avoid making the ultravisor unhappy. Same for the program status word. Only the interrupt bits are saved, and the wait state. The wait state is needed because the hypervisor needs to know when a CPU doesn't need to be scheduled anymore. Another interesting thing is the condition code, which is write only. So when an instruction needs to set the condition code, the hypervisor can just set the condition code normally. The condition code is never saved from the secure VM to the hypervisor, and it's only read from the hypervisor when we expect one, and even then it's checked. Like, you cannot return 2 if the architecture only allows for 0 or 3. So this is checked. And of course, the pointer to the secure instruction data area is also in the state description. So what does the guest do? First, there is a bootstrap, which checks if these protected virtualization enhancements are available. It loads the encrypted blob, and then it performs this reboot, as I said before. What happens in the kernel? It checks if the ultravisor is available and performs a query function to discover, for example, if it's running as a host or as a guest. If the guest discovers that, or when the guest discovers that it's running as a guest, it needs to set up some shared memory, so to mark some memory as shared for the bounce buffer, and then use the bounce buffer. We use the SWTLBIO for VIT-IO. Let's see which changes then were needed in the end in the guest and in the hypervisor. Okay, this small change in the bootloader or in the bootstrap is, okay, first loading the blob and then performing this transition in secure mode. It's not much of a change, but it's there. Changes in the guest, as I said. The architecture had been designed for to require the smallest amount of change. So apart from querying the ultravisor and then doing these shared buffers, there's not really much to do. One note is that the guest will run in keyless mode. If you know anything about the s390 architecture, storage keys is a very, very important part of the architecture, and secure guests will not have storage keys. All this has been already upstreamed. This is already upstream. Changes in KVM. So this requires changing actually the boot process of Linux itself, because we have to do this query ultravisor information and memory donation. This memory donation has to be done very early at boot. Then the memory access IO CTLs for Qemu. Sometimes Qemu will try to write into the guests, and it will not write directly into the memory, but it will pass through the kernel to avoid synchronization issues. What we are doing here is to cheat, and Qemu will think it's writing somewhere, but instead we are writing into this secure instruction data area. Of course, interrupt injection needed to be changed, and several instructions in the special handling. In some cases, because they are handled by the ultravisor, but there's still some notification that happens. In some cases, because they really need to behave differently. And of course, the ultravisor calls, they're sprinkled all over the life cycle of the virtual machines. The patches have been sent to the mailing list last week. So it's not upstream yet completely, but the discussion has started. We have had some comments already on it. Finally, what needs to be done in QEMU is to add the support for this reboot in secure mode, and to fix some instructions, because for some instruction QEMU was actually writing directly to memory, and this time it needs to go through KVM so that it can write into the secure instruction data area instead. Some conclusions. First of all, what have we learned, or what improvements have we done in general? Since this touched a lot of points in the architecture, we found some bugs that were there already, and we in general improved the overall compliance of QEMU and KVM. And to do swap and migration, which is just two bullet points, I know, but it's a lot of work. We actually have some idea of how to do swap, and we're still working on migration. And that's it. Questions?
I have two questions. One is for the normalization and all those things. How much of that is done by the ultravisor, and how much of that is done by the microprocessor or microcode?
That's implementation detail. So
as much as needed to not make performance suck.
It's done as much as needed as it's needed to work.
Yes.
And today is something, tomorrow can be something else. So doesn't really make a difference.
Yes. And then the second question, can you go one slide back, I think? Yeah, so migration, right? Because I forgot myself what I was going to ask. So for live migration, is there already some service planned in the ultravisor to help with that?
Not really at the moment. There's something we want that they can tell you we want to do that. Yeah. Eventually, but
because I'm thinking of x86, and there are some things that are done in a much more strict and complete way than, for example, the AMD extensions for secure virtualization. On the other hand, AMD was already planning for live migration from the beginning in the first iteration. So.
I'm going to preface this with I know nothing about S390, so I apologize if anything is stupid. You mentioned that you have to have the guest share memory to the host. Is there anything there on the KVM software side that could possibly be reusable for x86? Because doing similar things requires similar concepts.
What do you mean?
In the sense of this concept that QEMU can no longer see portions of guest memory, but can see portions of guest memory.
Okay, it goes in the other direction. AMD is doing that for SEV. They are using bounce buffers.
But you mentioned that you need share. But the guest needs to share memory.
But let him talk.
I did the guest support, and basically we are piggybacking on the infrastructure introduced by AMD. So they did it first, and we are plugging in and doing what we need to do differently, but basically the most work was already done.
Thank you.
So a couple of questions. I understand that on Z you actually have two levels of hypervisor. You have an LPAR level, and then you have KVM running on top of that. Now, you were just using the term hypervisor, and you're talking about donating memory that's absolute memory. Is it KVM that knows about absolute memory and can donate that, or is it the LPAR level?
It's absolute in terms of the configuration, so it's absolute for the LPAR guest. It's not system. It's not system absolute, as in the whole thing absolute.
Okay, and the second question is that you talked about being able to do I/O. Now, is that S390 specific I/O or is it VirtIO? Because on Power we have exactly the same issue.
It's VirtIO, but it's not VirtIO PCI. It's VirtIO CCW, which is the same concept, but instead of having a PCI device as a proxy, you have a channel device as a proxy. Because you must still need to have the ring buffers mapped with an IOMMU or something to do the bounce buffering on all the data that is being transferred through the VirtIO device. How do you arrange that bounce buffering? Is that just we are using the SWTLB-IO like AMD is doing for bounce buffering. I mean, he implemented most of it, so maybe he can tell you more. But we didn't really need to do much. We just reused the already existing infrastructure for bounce buffering.
For the channel programs, we actually don't have IOMMU because it's solved differently architecturally. Actually, in hardware, I think we do have somewhere deep below an IOMMU, but that's again an implementation detail.
And anyway, any small buffer that is needed for this kind of I/O, like descriptors that are passed, would normally describe which kind of I/O is to be performed. These small buffers are actually bounced to and from the guest using this small bounce buffer that is handled by the ultravisor. So when doing like channel operations, that small buffer that is like a few hundred bytes is copied to and from this small, very specific bounce buffer, this tiny kind of bounce buffer thing, and by the ultravisor. So if that answers the question, I don't know.
Okay, thank you. We're running out of time, so maybe the next questions can be like in the hall.
So I will be around anyway, and today and tomorrow. So if you have any questions, just show up.
Thank you.